Hello everyone. So today we are going to discuss the reflection and transmission of an electromagnetic wave in the dielectric media. And for the sake of simplicity, I will assume the case where the electromagnetic wave is incident normally to the plane of propagation. Okay, so what does it mean? That suppose we have this plane and this is how the electromagnetic wave is coming. Okay, and as you already know, there would be, so this is the direction. So my fingertip would point out the direction of the propagation, which is the z direction, and then we will assume that the x direction has the electric field and y direction carries the magnetic field. So with these things, now imagine that this is the boundary region. So obviously, so what we will do the following. So this is how my electric the wave is coming. Okay. So this is the direction of propagation. This is my k vector. So imagine that the original vector is k0 and r log, and then this is the direction for the electric field. Imagine that this is E0 and this is the direction of the magnetic field, say V0. Now this will get partially reflected from the surface and partially it will get refracted or transmitted. So let's assume that E1 is the part that returns back post reflection. So obviously now the E0 component will point downward to the direction of x. So that means this is where we will write E1. That's the percent, that's the fraction of E0 that's reflected back. Similarly, this is going to be the direction of propagation. And again, this direction of propagation is essentially going to be the same. So imagine for now, this is K1. And the B vector would point like this. Okay. Similar thing would happen with the transmission. So let's write the transmission part. So we will have the E vector. So of course during transmission the direction doesn't change. So imagine that this is the E2, that's the part refracted part of the electric field. This is the refracted part of the magnetic field, and this is the direction K2 vector. Okay. By the way, all of them are the vectors. If you wish, you could write actually these as H's. Okay, H2, H1, and H0. That's also fine. So now we need to obviously, so because these are two different media, they will have different values of the dielectric constant as well as the magnetic susceptibility. What does it mean? That mu over here say is the same, similar over here. So this is mu1, this is mu2. We could assume that epsilon is epsilon1 over here, and in this case, in fact, this is mu is mu, mu. Okay, so mu remains the same. Say mu1, mu1, or whatever, or mu1, or mu2 is mu, mu1 is mu. Epsilon is epsilon1. Epsilon1 is epsilon. Epsilon is epsilon1 and epsilon is epsilon2 over here. So n1, that's going to be, in fact, we will assume this to be 1 for the sake of simplicity, and it hardly has any role. So n is going to be epsilon mu, so that's going to be root epsilon. In this case, this is going to be root epsilon. Okay. So now, in order to solve this problem, we need to, in fact, before that, let me just try to write. So obviously, this will follow the plane wave form. So therefore, we could write the values of electric and magnetic field. So what would be the E0? E0 is going to be, suppose the direction vectors for these x, y, and z direction are the ex hat, ey hat, and ez hat. These are the unit vectors. So we will write ex hat, e naught naught, e to the power I, and let's write k0 K0, or rather if you wish, because K is also going to be in simply N1 omega by C. So that's going to be the same for both of them. So if you wish, you could write this as K1, this is also K1. And in this case, the K is going to be N2 omega by C, which is essentially the K2. So this is going to be e to the power I K1, and then the direction of propagation is z. So that's how you will write. E1 would be written as, again, the direction is changed. So this means we will have minus Ex at E1 naught, e to the power I, and the direction of propagation is also reversed due to refraction. So therefore this is going to be minus I K1 jar z omega t. Similarly, E2 naught, that would be written as, well, the direction remains the same. However, we will have the K get changed. So this is going to be e to the power K2 z minus omega t. So this is my equation 1.1, 1.2, 1.3. Now what is B? Well, we already know that B is nothing but n hat, right? So this is n, and then the direction of K vector, n direction of K vector, and then we have the electric field. So therefore we could write these things as well. So E B naught, that's going to be Ex, and then what is n? N is essentially n1. K hat vector. What is the direction of K hat? That's the z direction. So this is going to be Ez cross E1 naught and E naught naught. So this is going to be E naught naught, and then, I'm sorry, let me just write the form. This is going to be Ex naught, then E naught naught, and I'm sorry, there shouldn't be these vectors because I had already written the direction. So this is going to be E naught naught. These are just pure amplitudes. So this is E naught naught e to the power I K1 z minus omega t. So therefore this is going to be EZDX is going to be ZXY. So this is going to be EY, and this will survive. So this is N1 EY hat and E naught, this whole thing. So this is going to be e to the power 0, 0, e to the power I K1 z minus omega t. So similarly we could write B1 naught and B2 naught. So let's see the what B2 naught would be. Again you will have the N1 as the refractive index. However, the K vector gets changed. So this is going to be minus Ex vector, and then we have, I'm sorry, this is Ez vector and cross Ex naught. So that's also minus Ex hat, and then we will have the whole thing EZZ. Okay, so sorry, I'm sorry, it's going to be E1 naught e to the power I K1 z minus omega t, and therefore this is going to be equal to, well, minus minus plus, and zx is y, so n1 e to the power y e1 naught e to the power I K1 z minus omega t. Similarly, v2 naught, well, that's going to be the straightforward thing. We will have n2 e j dy ex e to the power I K2 z minus omega t. So these are my equation number 2.1, 2.2, 2.3. Now, in order to solve this problem, what we need to ensure is that the boundary conditions are satisfied at the surface. Okay, this is the boundary point. So what should be the boundary condition? Boundary condition should be the following. Boundary condition says that the periodicity, number one, the periodicity E and H must be periodic, which they are. Okay, let me write the boundary conditions. And then the second, so this is a must-have condition, no matter what problem we study. And then the second problem is that the tangent and normal components of E and H must be continuous. So what does it mean? It simply means, so this implies that E vector should get added, because what is the direction of the normal? So the tangential direction is what? So this means that's the tangential direction. That's how your E vector is going. So all these parallel vectors should remain the same. So what is happening here? What we have is E naught naught as the incident thing. Then we have the other one is E1 naught. However, it differs by a sign. So we will write E1 naught, and that should be equal to E2 naught. So that is my condition number 1. And for H or B, this is going to be simply H1 naught or B1 naught plus B naught naught. That should be equal to B2 naught. Or that implies that for us this is going to be N1 E0 0 plus N2 E1 0. That should be equal to N2 E2 0, because these are the things we have. Okay, so these are the two equations, 3.1, 3.2. Let me write this in little bit appropriate manner and try to solve this. Well, so from here, the 3.1 and 2 can be rewritten in terms of E naught naught as, how do we write? So we will have E1 naught, that's gone on the other side. So this is my first equation. And then the second equation is E naught naught, N1 E1 naught, N2 E2 naught. So what I will do, I will divide this whole thing by N1 and take the things properly along a direction that they deserve. So we will have E1 naught minus N2 by N1, E2 naught, that's going to be minus E naught naught. Okay, so these are the two equations. So rather I could write prime, this is prime. Okay, so now we will simplify. So on simplifying, what we obtain? So what we will do, for the first case we will simply subtract, and what we will get, E2 naught 1 plus N2 by N1, that's equal to 2 E naught naught, or that implies E2 naught is equal to 2N1 upon N1 plus N2, that's 4.1. And if I just put this value into, say for example, this equation, so E1 naught is going to be E naught naught minus 1 minus 2N1 upon N1 plus N2, which is basically, or E1 naught, that's going to be N1 minus N2 upon N1 plus N2 E naught naught. So this is 4.2. Now let's see what happens to the pointing vector. So this implies the pointing vector. So let's try to calculate the pointing vector. S hat. What was it? It was C by 8 pi and real of E cross H star. Okay. So this would be C by 8 pi real of E vector cross H is basically N K hat vector and then we have B. So this is going to be and so this is going to be, and of course H and B are the same, so I'm not writing those things separately. So this is going to be NC by 8 pi real of, I'm sorry, this should be E. So E cross K hat and then E. So that means E cross N hat. That is what we need to calculate. So this is E, and in fact, so if we write it properly, so this is going to be real of E naught square, or rather this is going to be E naught square and then N hat. Well, we will have the simplifications in two terms. So, okay, so this is N hat K cross E. Okay, so these simplifications will result into one term like this, and another term is going to be simply E dot N hat cross E dot N hat dot E, and that would leave us, because E and N are normal to each other, so therefore this is going to be 0. So this is NC by 8 pi real of E naught square. So real of E naught square, or rather E naught square. So this is going to be E naught square and then N hat. So now what I will do, I will calculate the reflectivity, reflection coefficient R, and transmission coefficient T R. How to write the R? So R is going to be the ratio of energy that is pointing along the reflected direction. So what is the pointing vector for the reflected direction? That's say S1, and then what is the direction dotted with the direction? So what is the direction over here? It is Ez hat, and then similarly we will have S0 naught, and the direction is Ez naught. So this is going to be, now S1 would be NC by 8 pi, well N1C in fact, N1C by 8 pi E1 naught square, and then N dot. So what is the direction? This is Ez hat dot Ez hat upon, this is going to be also N1C by 8 pi, this is going to be E naught naught square, and this is Ez hat, this is also Ez hat. Okay, we will differ by a sign, however that doesn't matter. So in fact over here we have positive of both of them, and this is going to be negative in fact for both of them. So this is going to be minus Ez and minus Ez. So this is plus. So this is minus Ez, this is also minus Ez. So this whole thing is going to be positive. Okay, so from here what we conclude that R is nothing but E1 square, the amplitude of the reflected wave square upon the amplitude of the transmitted wave square. So that's going to be according to the relation 4.2 N1 minus N2 upon N1 plus N2 whole square. So this is 5.1. Similarly, we could have the transmittivity that's going to be equal to S2 dot N hat. In fact, this is again Z direction upon S0 dot Ez direction. So this is again solved. Well, we will have Ez, there is no problem. We will ultimately you should be able to get E naught square, E naught naught square, and that is going to be 2n1 upon n1 plus n2 whole square. So from here we could check one interesting thing. R plus T. Well, what should we expect? R is the fraction that is getting reflected and T is the fraction that is getting transmitted. So the total should be unity. Let's check whether that happens or not. So well, this is the thing over here, and this is what we have for the transmittivity. So obviously from here we will have minus 2n1, this is 4n1, so we will have n1 square plus n2 square minus 2n1 n2 plus 4n1 n2. Oh, I'm sorry, there should be n2 in fact. If you just check the expressions, we should have n2. So upon n1 plus n2 whole square. So this means we will have n1 plus n2 upon n1 plus n2 whole square. I think what went wrong over here is the following. So S2 will have n2. This will have n1. So therefore ultimately it should be 2n1 n2 upon n1 plus n2 whole square. So this is 5.2. Okay, so I am using the 5.1 and 2 to get this particular thing, which is basically 1. So therefore R plus T is 1. Okay, so this is equation 6. So this is the simplest case that we studied just, and we have checked that R and T are not independent. In fact, that should form the ratio. That summation should always be the 100%. That is the value for the incident wave. Okay, so this completes the whole thing. In the next time we will do more general case, which is where rather than considering the wave propagation along the g direction, we will have all sorts of general directions and we'll check how the things vary. Thanks.